So one benefit of knowing the specific relationship between two isomers is the insight it provides into their relative behavior, both their chemical behavior, and I just want to remind you chemical behavior are things like the products they form, reaction rates, equilibrium constants of their various reactions, and their physical properties, right? For example, like boiling point, melting point, and solubilities. Um, and so knowing these relationships really help us because we have some general rules that tell us whether isomers are going to behave identically or differently. So, constitutional isomers are kind of the first isomers that we started with, and constitutional isomers have different physical and chemical properties. Right? And how different they behave generally depends on the degree to which their connectivities vary. So, like for example, if we look at pentene, pent 1-ene here, or 1-pentene, what we find is that its boiling point isn't much different than trans pent 2-ene, right? They're different. Those are physical properties that are different. But if we look at the connectivity between but 3-ene 1-ol and tetrahydrofuran, which is often abbreviated as THF, it's a common solvent that you're going to see. We can see that these boiling points are much different, right? Part of the reason is because the way this constitutional isomer is, it can have hydrogen bonding while this one can't. So constitutional isomers are going to have different chemical and physical properties, and how different it is just depends on that connectivity. Now, enantiomers are another isomer that we talked about, and enantiomers, these guys are mirror images, and so they're going to have the same connectivity, and they have exactly the same polarity. So these have the same connectivity and the same polarity, exactly the same. So what we find is that in many situations, enantiomers generally behave identically. And so what we see here, for example, the boiling point is what we compared before. The boiling point here is 99 for this enantiomer of butane 2-ol, and this boiling point is 99 degrees. However, whether or not the enantiomers behave identically does depend on their chemical environment. So enantiomers traditionally are really hard to separate, but what we can do is we can change their chemical environment to make it easier to separate these enantiomers. So we have to define their environment. We can basically have two different environments. And most environments that we encounter in the laboratory are called achiral environments. This is an example, like when a pure enantiomer boils, right, most solvents, solutes react with enantiomers are achiral, right? So there's no interaction, right? Water's achiral. If you're boiling enantiomers in an achiral solvent, like there's not going to be any difference. So achiral solvents environment means there's no specific part of chirality there. And an analogy here that's shown, right, is socks and feet and shoes. And so when we think about this kind of analogy, a sock here has a plane of symmetry, and so it's achiral. And because a sock is in an achiral environment for the feet, a sock can fit on a feet in either foot, right? It doesn't really matter. But a shoe is chiral, and so a shoe that's a left-footed shoe has to fit on a left foot, and then a right-footed shoe has to fit on a right foot. So in chiral environments, and these can occur in a variety of ways, enantiomers have different physical and chemical properties. So for example, in chromatography, A chiral stationary phase can be used. In chemical reactions, we can use chiral catalysts that are just one enantiomer or the other. And probably most importantly, biological systems are chiral environments because every biomolecule, like protein, sugars, and DNA, are chiral and in the body are present exclusively in just one of the enantiomers. So, depending on the specific situation, the behavior of an enantiomer can be slightly different or dramatically different. But one of the things that we know is that it depends on whether the environment is chiral or achiral. Now, we also have diastereomers. Diastereomers are going to have different physical and chemical properties, right? So like enantiomers, diastereomers are going to have the same connectivity, but they aren't mirror images of each other, so they behave different chemically. One of the reasons they can behave different chemically is they can have different polarities. So for example, this is cis 1,2-dichloroethane and trans 1,2-dichloroethane. And their polarities are different. This is a polar molecule and this is a nonpolar molecule. So if you wanted to separate out these two molecules, you could maybe use different solvents, right? One that's polar or one that's nonpolar, and really depend on their solubility. Now, and you can see the difference here with their boiling points, but not all diastereomers are going to have dramatically different boiling points or dramatically different physical and chemical properties. And so, for example, 2S, 3S butane 2,3-diol, we're going to see that these have really similar properties because there isn't a big difference in, say, their polarity. So they are going to have different physical and chemical properties, but the amount or how big that variation is depends on the individual structures. So one of the things that we have to do in a laboratory a lot of times is separate isomers. And so the first person to really come along and separate isomers was Louis Pasteur, which if you've been in biology, it's the same Louis Pasteur that did pasteurization. And he was the first to isolate a pair of enantiomers from each other. The enantiomers he looked at was sodium ammonia tartrate, and these crystallized out. And he noticed there was a left-handed crystal and a right-handed crystal, and he used tweezers and separated these guys. We don't use tweezers. Instead, since diastereomers have different physical properties, we separate by common laboratory techniques like distillation, fractional distillation. Right? If they have different boiling points, we can use those boiling points to separate those out. If they have different solubilities, we can separate those diastereomers by crystallization. We can also use chromatography with different polarities, right? So those are some ways that we can separate our diastereomers. Now, enantiomers can't be separated by these methods in an achiral environment, right? So we have to be in a chiral environment. So we have some different methods for separating enantiomers. Because what Pasteur did is just not really feasible in most situations. And so you can, here's three kind of methods, but there are lots of methods out there. People publish research all the time on ways to separate enantiomers. You can temporarily convert the enantiomer into a pair of diastereomers, and so those will have different physical properties. You can separate the diastereomers from each other and then regenerate the enantiomers from the separated diastereomers. This was some research that I did when I was an undergrad, and we were looking at using different kinetic rates to separate out enantiomers. So lots of different ways that are currently being investigated to do that. Now, although enantiomers have identical physical and chemical properties in achiral environments, they behave differently in chiral environments, and they also interact differently with plain polarized light. Okay. Light, and this is just a quick review, light can be regarded as both a particle and a wave. And so when it's treated like a particle, we think of light as consisting of photons. And then when it's treated like a wave, we think of light as consisting of oscillating electric and magnetic fields. And then the frequency, of course, of that oscillation defines that frequency of light for us. And so that's what's being shown here is the oscillating, which just means we're going up and down, electric and magnetic fields. As the ray of light travels through space, its electric and magnetic fields are going to oscillate in planes that are perpendicular to each other, right? So this goes this way and this comes and intersects this way. If all the photons from a light source have their electric fields oscillating in the same plane or in the same direction, that's called plane polarized light. Your sunglasses do this a lot of times. Certain camera lenses will do this. And I'll have an example in class. A red double-headed arrow, right, like this, is used to represent that plane of polarization. And the plane where the magnetic field oscillates is perpendicular to the electric field's oscillation. And that's just known to us. So that's plane polarized light, okay? Now, most light sources emit a light that's polarized. And so what we need is a polarizer, which generates plane polarized light by filtering out light whose electric field oscillates in any other plane. So basically what you have is from your light source, we've got ordinary light where the photons are just oscillating in all sorts of different planes, or the electric fields, right, are pointing in all sorts of different directions. And then we use a filter, which is called a polarizer, which basically only lets the light through that's oriented in one way, okay? And that's, when we talk about plane polarized light, that's what we're talking about. We have filtered out all of the other light that's going in all sorts of different directions. Now, we said previously that once you get plane polarized light like this, enantiomers will rotate in different directions in plane polarized light. So what happens here is you take plane polarized light, okay, and you pass it through a sample of a compound here, and depending on whether the compound is chiral or achiral, it will rotate, okay? So you have your plane polarized light, it's rotated as light passes through a tube, right, containing the chiral optically active compound, and then the plane of polarization of the light exiting the tube is measured and compared to the initial polarization, and that's alpha, and that tells us which way it rotates. We have polarizers in the lab, and we will do an experiment based on this. So we'll be able to see different molecules and how they rotate in plane polarized light and whether they are chiral or achiral. Now, a few things. The angle where the compound rotates is called the measured angle of rotation, and it's represented with a lowercase alpha, and it's just obtained using an analyzer, and the analyzer for us is going to be vernier. Then the light enters the analyzer after it exits the sample, okay? And so chiral compounds that rotate clockwise, which is defined as the positive direction, are called dextrorotary. Let's pretend like I can spell that right. Rotary, okay? And those that rotate in the light counterclockwise in the negative direction are called levorotary. Okay. This does not correspond to S or R, right? And you can only figure this out using an experiment. Okay. And so that's one of the things that we'll experiment with in lab. Now, there's some factors that can govern the angle of rotation. And so what we, of course, are interested in is the specific rotation, right? And so one of the things that we know is as the concentration of a chiral compound increases, so does the angle of rotation. And then as the length of the sample increases, so does the angle of rotation. So the concentration and the sample tube are going to influence this. And so we can calculate the angle of rotation using the specific rotation, which is a constant that's unique for a chiral compound. And so basically, we compute this. We can calculate this. So for example, if we go into the lab and we measure this, and we know the length and the concentration, then we calculate this. And then for no matter which sample you have or where you are, once you take the length of the tube, the concentration, and the angle into consideration, you can get the specific rotation, right? Enantiomers are going to have equal but opposite specific rotations. So that's one of the things that we're going to see. Now, we call a racemic mixture a mixture of both enantiomers. And so that's going to contain equal amounts of the positive and negative enantiomers. When that happens, they cancel each other out. The positive and negative rotations cancel each other out, and it looks like there's no rotation at all. So if you have a racemic mixture, equal amounts, that's what we call optically inactive. There's no rotation there. If a mixture of enantiomers is not racemic, then it will be optically active. So you can have more of one enantiomer than the other, and that's called enantiomeric excess. So you can have a 50-50 mixture of two enantiomers. That's a racemic mixture. You can have a completely pure solution of just one enantiomer, and that will give you, say, the positive or the negative, depending on which enantiomer you have. But you can also have a mid-ground where you have an excess of one enantiomer over the other, and that will affect the angle of rotation. And so we can measure that. The specific rotation of a mixture equals the enantiomeric excess times the specific rotation of the pure enantiomer divided by 100. Because that percent EE is divided by 100, this is going to be a fraction between 0 and 1. So what happens here is the specific rotation of the mixture of enantiomers is smaller in magnitude than the specific rotation of the pure enantiomers. So let me put some words to that. The specific rotation of a mixture of enantiomers must be smaller in size than the specific rotation of the pure enantiomers. Okay, and this is what we observe. You might ask yourself, why is this really important? Well, it turns out that because our bodies are chiral environments, then enantiomers interact differently with our bodies. The best example of this is thalidomide. Thalidomide was a medicine used in the 1950s in Europe to treat morning sickness. It was chiral, and the medicine was given with both enantiomers, this enantiomer here and this enantiomer here. It was known to suppress nausea, so it was given to women who were pregnant. But what happened is this enantiomer causes birth defects. It attacks rapidly dividing cells. So you had babies that were born without arms and legs and hands. And so that really pushed science to begin to have enantiomerically pure medicines if the two enantiomers interact with the body differently. And so it was estimated that more than 10,000 children worldwide were born with deformed or missing limbs. Now, one of the things to be aware of is this is now used for some cancer treatments because it attacks rapidly dividing cells. So we have lots of chiral centers and biomolecules. When you go to biochemistry, you're going to see that amino acids have chiral centers. That means all your proteins are going to be chiral. Your sugars are chiral. DNA has chiral centers. Hormones, right? Your lipids have chiral centers. So most natural amino acids, monosaccharides that appear in the body, are exclusively in one enantiomeric form. And so that's why medicines tend to react in a certain way. Different enantiomers react in a certain way is because your body is achiral. This for us finishes chapter 5. The book goes into a little bit more into depth in some biomolecules, which if you're interested in that, you're more than welcome to read, but we are going to stop here. And so we have finished our journey through enantiomers, and we will pick up with acid-base chemistry in chapter 6.